All right. Our next speaker is Stacy Malaker. She's an assistant professor with the Department of Chemistry at Yale University. Her lab is focused on establishing methods and technology using mass spectrometry to study mucins, which is a class of densely oglycosylated extracellular proteins. Malaker's group also studies mucins in a biological context because they're involved in a lot of disease states and other processes, but aren't very well understood how they work there. She received her BS in biochemistry and anthropology zoology from the University of Michigan and went on to do a PhD in chemistry from the University of Virginia, followed by a postdoc at NIH under Carolyn Bertozzi. Stacy, thanks for being here.
Well, thank you for that introduction, and thank you all for being here today. I'm super honored to be on the same stage as so many rock stars. Looking forward to speaking with you all later. So yeah, my name's Stacy Malaker. I'm currently at Yale, but I'm going to kind of tell you my life story. So I grew up in Metro Detroit, and then I did my undergrad at the University of Michigan. Max will have words later. And then did my PhD at UVA before doing my postdoc at Stanford, and started my lab at Yale in 2021, so also at the height of the pandemic. So I grew up, like I said, in Metro Detroit. This is actually the house I grew up in. That was my bedroom. One of 3 kids. My dad was an engineer at a tool and die factory, like all Detroiters related to the automotive industry. My mom was a stay-at-home mom. So I'm actually a first-generation college student, and you'll kind of see throughout this that I made a lot of decisions based on my gut and my interests. No one really, told me you had to go and be a scientist. I just sort of followed that path. You'll also notice that my older brother has Down syndrome. So I knew from a very young age that when my parents get older, that I will be his caregiver. And so that was a very strong driving force in my life to succeed and have stability so that, when that time comes, I'm able to provide for him. Also, he's awesome. And my sister's okay too. So like I said, I ended up going to the University of Michigan. I'm a die-hard Michigan fan. I have cried more tears over Michigan football than any failed experiments. So being a first-gen, low-income, I had to work a couple jobs to keep myself afloat. My first job was at GFS Marketplace, and if you're from the Midwest, you may be familiar. It's kind of like a bulk food store, not quite Costco. And though I've won a number of scientific awards, I would say one of my proudest achievements to date is that I won Stalker of the Year one year, and they gave me a golden box cutter. And this actually was taken a week ago. It's in my office at Yale. But in addition to working at the grocery store, I also worked in a core facility where we did peptide synthesis. And that was run by Dr. Henrietta Remmer. This is really where I got my scientific beginnings. And of course, like I mentioned, we did peptide synthesis. But this is also where I first became familiar with mass spec. So we used mass spec for quality control just to check that we actually had the peptides we wanted. We also did Edmond degradation, which by now is basically a dead technique, but we used it to sequence our peptides. And I also got familiar with basic biochemistry techniques like SDS-PAGE and IEF and so on and so forth. So after 4 years, it was time for graduation, and here's me taking graduation very seriously. And after I graduated, the question became, okay, what do I do next? And so, I thought about med school, but to be honest, I really didn't have the grades to go to med school, so that was out. I thought about farm school, but I wasn't super passionate about it, so that was out. I thought about getting a job. I worked in a core facility, I have this experience, but I graduated in 2009, and the height of the recession, no jobs, especially in Detroit. So I thought about it, and I was like, I really liked CSI growing up. That lab seemed really cool. So why don't I go to grad school? And so long story short, I ended up at the University of Virginia, and I joined the laboratory of Don Hunt. If you're not familiar, Don is one of the founding fathers of biological mass spectrometry, basically developed the field. And he took me under his wing from day one. I absolutely loved working in his lab. And though he looks very serious there, he is a total goofball. This is him trying to open a champagne bottle. it was unsuccessful. Now, I learned a number of things in grad school. One of the most important things is basically how to take apart a mass spectrometer and put it back together. So I'm a mass spectrometrist, by trade. But I also got introduced to this little field called glycobiology. And so this is really where I got my feet wet, learning about different glycan structures, and in particular, how different glycan structures can modulate the immune system, basically how you can turn on and off T cells or B cells, and so on and so forth. So that really piqued my interest in glycobiology. And this, again, came time for graduation. And again, this is me taking graduation very seriously. And so, again, the question became, well, what do I do next? At this point, I was neck deep in sugar, and I was really, really interested in carbohydrates, to the point where my thesis Don basically said, I know you're super interested in this, but I never wanted to work with carbohydrates, and I really think it's time for you to leave and do a postdoc. My dedication goes so deep, I have a tattoo of glycan backbone, as you can see here. So I cold emailed someone at Stanford. You may have heard of her, little known person named Carolyn Bertozzi, total rock star. And if you haven't heard of her, here's her receiving the Nobel Prize last year. Now, the timing of this could not have worked out any better. Carolyn had just moved to Stanford and really wanted to invest in mass spec. So she basically handed me $1 million and said, go buy a mass spec and get it up and running, which is exactly what I did. But more importantly, in Carolyn's lab, I got introduced by this class of proteins called mucins. Now, mucins are characterized by having a high proportion of prolines, threonines, and serines in their so-called PTS domains, which I often refer to simply as mucin domains. Now, within these domains, most of those serines and threonines are modified by glycan structures. And that contributes to this really, really interesting secondary structure that's dense and rigid and what we call bottle brush-like because the glycans kind of stick out of the protein backbone. Now, there's a canonical family of mucins. So mucin 1 is MUC1, and mucin 2 is MUC2, and so on and so forth. And we have about 20 in humans. Now, we know that this canonical family of mucins is tied to pretty much every disease, but most notably in cancer. So to be sure, over 90% of breast carcinomas upregulate MUC1. MUC16, which is also called CA125, is one of the only available biomarkers for ovarian cancer. And we know that these mucins are tied to pretty much every aspect of cancer progression, immune evasion, metastasis, chemotherapy resistance, so on and so forth. But what we don't know is what mucins look like at the molecular level. So what sites are modified by what glycans in what different patterns and what different cellular states or diseases. And the reason why we don't know this is that mucins are basically impossible to study, especially by mass spec, which again, this just happens to be what I do. So for those that aren't really familiar with the proteomic workflow, I just kind of wanted to walk you through it. So normally when we're doing proteomics, you take a protein or a group of proteins or a cell lysate, and you digest them into peptides, commonly using enzymes like trypsin. So that the resultant peptides then get separated by reverse phase HPLC. We electrospray ionize them into the mass spec. And what that gives us is what's called a full mass spectrum, or an MS1. And that's basically a snapshot of all the ions that are going into the instrument at that given time. And then normally what we do is we take the highest abundant thing and we subject it to collisions with inert gas, usually helium or nitrogen. And that basically blows apart the peptide and results in what's called an MS2 scan. And that MS2 scan is basically like a puzzle. The way that it falls apart allows us to build back the sequence and figure out what's actually in your sample. But in one mass spec run, we probably get 50,000 spectra, so it's untenable to do that all by hand. So we often rely on search algorithms to tell us what's in those samples. Now, mucins make literally every aspect of this more challenging. So call me a masochist or a genius, I don't know yet, we'll find out. So I just wanted to kind of highlight some of those issues that we face. So basically, mucins are incredibly heterogeneous. So each serine or threonine might have 100 different glycan structures present. Now, if there are thousands of sites of modification and hundreds of different glycan structures, that combinatorial explosion of possibilities makes it so that the search algorithms don't work. And we have to do almost all of our data analysis by hand. Additionally, I mentioned that we bombard the peptides with gas molecules. Now, if you bombard a glycan with a gas molecule, it falls off. So that makes it so that we can't actually figure out what glycan structures were there, necessitating different types of fragmentation. Related to the heterogeneity is that unmodified peptides get into the gas phase easier than these glycopeptides. And if we can't get it into the gas phase, we can't actually figure out what was previously there. And finally, mucins are actually resistant to proteases like trypsin. And if you think back to the previous slide, that's basically step one of our mass spec workflow. So if you were to digest this mucin with trypsin, you would only get this N-terminus and the C-terminus, but this entire mucin domain would actually remain intact, and you lose all of that information. So when I started my postdoc, we hypothesized that due to the ubiquitous nature of mucins, that there had to be an enzyme or a class of enzymes that could actually selectively digest along the peptide backbone. So enter sticky. Sticky is secreted by E. coli in the gut to chew your gut mucins so that the E. coli can actually get into the cell. So we went through and characterized sticky, showing that it is what we call a mucinase. It's a protease that's selective for mucin proteins. I also went on to solve its cleavage motif, showing that it cleaves in a peptide and glycan-specific manner. Like the glycans have to be present, and this peptide sequence also has to be there. Now, this was a unique contribution to the field at the time. It doesn't seem like that big of a deal, but we were actually able to finally digest these mucins for the very first time. And so then we basically used sticky for everything we could possibly think of, including obviously improving mass spec analysis, clearing mucins from the surface of cells so that you could do downstream biophysical or biochemical assays. We also used an inactive point mutant of sticky to turn that into a staining reagent for IHC, flow cytometry, and Western blot. An extension of that, we turned it into an enrichment tool to pull out mucins from complex samples like ascites fluid or cell lysate. And then most recently, graduate students in Caroline's lab have developed sticky into a potential cancer immunotherapy. So this springboarded myself to my lab at Yale. And I need to give a shout out to this wonderful crew of humans. And I also need to give a shout out to our honorary group members. This is Queen, and that's Freddie Mercury, and this is Prince. So these do a lot of our work here. And my lab is basically focused on tackling all of those challenges that I just mentioned and really making it possible to study mucins at the glycoproteomic level. So we're doing this in a bunch of different ways. One is developing ionization techniques that augment glycopeptides to get into the gas phase. We also work on new enrichment techniques to selectively isolate mucins and glycopeptides from unmodified stuff that we don't really care about. We're also developing our own software because right now the data analysis is so time-consuming, and that's a real big bottleneck in our work. And basically, our goal is to be able to, as I said, sequence these mucins at the glycoproteomic level. This is a diagram of MUC16, that CA125, the ovarian cancer biomarker. Now, the biomarker currently only focuses on these unmodified regions. And so we want to sequence this to develop better diagnostic tools. We also believe that we can use this for improved therapies as well. So with that, I would like to again thank my lab, my funding, C&E News, all of you for your attention, and I'd gladly take any questions.
Thanks, Stacy. Great talk. I see in the magazine that you listed one of your proudest that you really enjoy kickball.
That's true, yeah.
Do you maybe have anything to say to the audience about kickball?
Sure. I was a mean pitcher, and I won 5 championships in Charlottesville during grad school. And I also broke my nose playing as well. Yeah, It was a nasty accident. I bunted the pitcher, threw it in between my legs, and I landed face first. But I pitched the last inning.
Oh, that same game?
Yes.
Hell yeah! Thank you.
Yeah.
Well, I was curious to ask the AI question, because it seems like large language models would
We're
be
working
a
on
pretty
it,
good
yep.
fit. So, yeah, what do you see that's exciting you in that area?
Yeah, so there's a researcher at the University of Gothenburg that is just doing incredible things with machine learning for glycomics, which is the study of released glycans, and we're now working with him to do glycoproteomics. So it's a work in progress, and so far it's moving really quickly, so we're hoping that comes to fruition.